Today I want to speak specifically about capacitance and capacitors. I'm passing out some capacitors. What you have right there are what are known as electrolytic polarized capacitors. We're going to be starting circuits quite soon because we're going to have capacitive circuits as our first, but we need to know what a capacitor is and how a capacitor behaves. So I want to start here by talking about how you can figure out what the capacitance of a capacitor is. You have to be able to derive this. And you have almost all the skills to do so. We just need to package them now. The definition of capacitance is charge per unit volt. What we would like to have is a way of knowing the capacitance of a device based on its physical parameters. This is the definition of capacitance based on usage. We'll use this in what's known as like Kirchhoff's equations, which help us understand how circuit elements behave in a circuit. But this is the usage equation for capacitance. It is the definition, is where we got the units and all that from. But ultimately, remember, what a capacitor does is it stores charge. What we would like to know is, how does the construction of a capacitor affect its ability to store charge? Meaning, I want to take this and translate it into something about the physical size of the device. The physical parameters. How do you build a capacitor? What parameters will allow you to have a higher capacitance of a capacitor? The first kind of capacitor we're going to start with is a parallel plate capacitor. And although I'm drawing this very two-dimensionally, I think you can imagine that what we're looking at here are two plates of metal, and I'm just looking at them on their side. Does that make sense? So I don't have the capacity to draw this particularly well. I will spend a few seconds to try and give us that impression, but I don't want to spend a long time on it because regardless of what I do here, they're not going to look great. So this is the idea here. I guess that's the best I can do. A parallel plate capacitor. There are some defining properties of parallel plate capacitor. There's the separation distance between the plates and the area of the plates. The only part that actually has capacitance is the part where the plates overlap. So we're going to draw these in such a way that the entire area of one plate is overlapping the entire area of another plate. Now, remember, the whole point of a capacitor is that we measure it based on how much charge can be moved per volt. So in order for us to measure the capacitance, what we're going to kind of do in our head is say that our capacitor plates are already charged. So this side is the positively charged plate, and this is the negatively charged plate. So we start this process by saying, step one, the plates are charged. I don't know how to say this otherwise, but it's not always plates. You know, we already know that there's three different basic types of capacitors. We have parallel plate capacitors, we have cylindrical capacitors, and we have spherical capacitors. So when I say plates, meaning like the sides, like if it's a cylindrical capacitor, we're talking about the inner wire and the outer wire. If it's a spherical capacitor, we're talking about the inner shell and the outer shell. So I'm saying plates, but what we really mean is that two parts of a capacitor are going to be charged. We're going to be taking charges from one and depositing them on another. So in some other process, these plates have been hooked together by a potential difference, and charge has been allowed to flow from one plate to another. That part has already occurred. So we're beginning with the plates charged. The next step is to determine the electric field due to the charge. Now, we've spent a lot of time learning about the electric fields that are produced by various shaped types of charges. So the parallel plate, we already know what the electric field is due to a parallel plate. But in general, this is usually something that we would use Gauss's law or Coulomb's law to work out. On a test, you'll likely have to show your work. But we've already done the parallel plate, and we've done two parallel plates of opposite charge. So we kind of already know what the electric field should look like between these two plates. Now, I'm assuming you remember that conversation. So assuming you do, then we should all be in agreement that the electric field between these plates has to do with the charge density. We know it's uniform, and we know since we're dealing with an infinite sheet of charge, one of these sheets will have an electric field that is sigma over 2 epsilon naught. And since we have two of them, the electric field between the plates should be sigma over epsilon naught, right? Twice the contributions. We've done this problem before. You should go back in your notes and remind yourself how to do that, because I'm going to expect you on a test to be able to show the Gaussian surface you would use and how you would come to this conclusion. And you've already had this as part of your test, so you know what I'm talking about, right? Like I said, when we're doing this, the idea is to come up with what our value is for the electric field. Now, in this particular example, this won't be the electric field because it's in terms of sigma, but we don't have a sigma to use here. So we'll have to replace sigma with something that makes sense for this situation. We're bringing in what we know about an infinite sheet, and we're applying it here. So in this example, sigma over epsilon might be our electric field, but for us, we'll have to write that as Q over A over epsilon naught, where Q over A is our sigma, our charge per unit area, where A is the area of the plates. Excuse me. So again, step 1, charge the plates. Step 2, determine the electric field due to the charge. Step 3 is to calculate the electric potential. From the negative plate to the positive plate. So our step 3 is to calculate the electric potential from the negative plate to the positive plate. This will be using V equals minus the integral E dot dr to go from the negative plate to the positive plate. So we have a parallel plate capacitor. Our parallel plate capacitor has a region that has a uniform electric field. Because of that, we know that the electric field is a constant between the plates, and we just spent a few minutes reminding ourselves what that constant is. For us to actually do step 3, we're going to start at the negative plate and go towards the positive plate. Right? Now, that means we're going against the direction of the field, but we know that the electric field between those plates is Q over A epsilon naught. So we're going to start with negative integral Q over A epsilon naught dr. We're going to set our limits based on R. And we're going from the negative plate, we're going to call that 0, to the positive plate, which is a distance d away. Good. So does that make sense? See why we're doing that? We're picking one plate, making that our reference point, and we're going from our reference point to our destination, which is the positive plate. Now, the truth is, we don't have to go from the negative plate to the positive plate. I could just say at the end of this, make sure you take the absolute value of the electric potential. We just need to know what the electric potential is between the two parts of your capacitor. But by going from the negative plate to the positive plate, you guarantee a positive answer. Does that make sense? All right. Either way, that's what we're going to do. Now, again, you have to guarantee a positive answer. Remember that this is a dot product here, correct? So in the case of our problem, this is the electric field times dr times the cosine of the angle between the direction we're traveling and the direction of the electric field, which for this problem is 180 degrees. Right? Because dr is going to be in this direction. The electric field is going the other way. Now, clearly this is going to be a pretty straightforward integral. This one is going to be easy. I can pull out my constant. I can just leave dr here, and the negative cancels. Right? Cosine 180 is a negative sign. Negative times negative cancels out. And we're going to evaluate this from 0 to d. Sorry, I'm not sure why I left dr in there. It's just r in there. So that's going to make this q over a epsilon naught times d minus 0. And finally, that means that our electric potential is qd over a epsilon naught. So again, we charged the capacitor. We found the electric field between the plates due to the charge on the plate. We've calculated the electric potential by going from the low plate to the high plate. 3 steps. When you're done, you should have an expression for the electric potential due to your capacitor. This is our expression for the electric potential due to our capacitor. There's only one thing left to do, and that's to plug it into the formula for capacitance. Once we've done all these things, we're trying to find an expression for capacitance that's based on the actual structure of the device. So our definition for capacitance is the amount of charge divided by the applied potential difference. We've done this in the reverse. We've said, what is the potential difference if you already have a charged capacitor? But that still gives us the value for the capacitance. So I take the charge that we already have, Q, and I divide by the definition of the electric potential that we just derived, which is QD divided by A epsilon naught. Now, this part should be pretty clear. The Q's cancel out, and we're left with an expression for the capacitance that is A times epsilon naught over D. Now, I don't put a lot of, stock in this, derivation, because although this was a derivation, it wasn't particularly hard. The other ones are going to be harder. The cylindrical and the spherical are going to be more difficult. This one's nice because it's got a nice uniform electric field. But there are some obvious things here that all capacitors will share. If you'll notice, 2 things really control the size of the capacitance: the area of the plates and the separation distance. And no matter what type of capacitor we have, those are the 2 things that will determine the capacitance. If you want to make a capacitor with more capacitance, you need bigger plates and you need them close together. That's what all capacitors will share. No matter what their structure is, no matter how they're made, if you want to make a capacitor with more capacitance, bigger plates, put them close together. Everybody got it? That's what all of them are going to look like. So when you've done the math for a cylindrical capacitor, if it doesn't follow that, then you made a mistake. It will follow that rule. So every time getting the plates closer together will increase the capacitance, and having more overlap in the plates will give you an increased capacitance. Now, there are some limitations here. One of these things that we did is that we based it on what's known as epsilon naught. Epsilon naught assumed that there was a vacuum between the plates. If you could adjust this constant, then you can adjust the capacitance as well. That generally means filling the space between the plates with something else. All capacitors will fill that space with something that will make for a higher permittivity. And the first thing that I want you to understand is that the stuff that you put in between the plates of a capacitor has a name. It's called a dielectric. All capacitors use a dielectric of some sort. A dielectric manipulates the permittivity. It generally increases it. In fact, that's the goal, is you want to have something higher than the permittivity of free space. So dielectrics have a permittivity, so we would just leave that as epsilon. But that's not generally how it's done. Usually what we do is we all describe permittivity by comparing it to the permittivity of free space. So what we usually have is what's called a dielectric constant, a unitless constant that sits out front of epsilon, kappa. And the dielectric constant is just what it sounds like. It's a value that multiplies the permittivity. Kappa is, like I said, it's called the dielectric constant. It's almost always a value that is greater than 1. And for the most part, almost every material in nature has a dielectric that is greater than the permittivity of free space. So you can put just about anything between two plates and it will increase the capacitance. There's very few materials that disrupt the electric field and actually reduce the capacitance. Most capacitors are made by just oxidizing one plate of metal and slapping the other plate right on the oxidized side, meaning they get them very close together, just a couple of molecules apart. And whatever your oxidizing agent, whatever's deposited there, they just use that permittivity. The problem is that a parallel plate capacitor is going to be obviously big, right? Because you have to have plates that have area. You'll notice every one of these is going to have some function of size. Do your capacitors that you guys are holding, do they look at all like two plates? They're tubes, right? Little round tubes. The way you get those is you take two plates and you roll them up. That's how those are made. They have the two plates rolled together. One wire is connected to one side of the plate, the other wire is connected to the other side of the plate. They dip them in plastic so that they don't leak out, and that's how you get a cylindrical looking capacitor, but they're all parallel plate capacitors. All the ones that I handed you are all parallel plates. That's how they're made. So the two wires sticking out are sticking out from two opposite plates that are separated by some dielectric inside. All right, tomorrow we're going to measure the dielectric constant of paper.